All right. So let's do the last big topic, and then uh, next week, and then I guess we got 2 more days after that. Next week, I'll just kind of set you up for what's going to be on the final. And he starts this off. I guess I've never read this part right here, which I guess is a bad thing. Um, I guess it's not that bad. But he starts off by, you know, this is supposed to be water. It looks kind of funny. And you've probably experienced this before, that the deeper you go in water, the pressure varies linearly. And that you'll learn all this in fluids. That's basically the weight of the water for unit volume. So if you had an aquarium that was 1 foot cubed, it would weigh 62.4 pounds. So as you go down underwater, the pressure gets greater. So he lists this, and he says anytime there's a linearly distributed force over a plane, then when you work out the moment, you get a term that looks like this. And I probably should zoom in on it, and he pulls it out, identifies it, and calls the moment of inertia. But most places call it the area moment. When you get in mechanics and materials, they're going to call that area moment. They're not going to call it moment of inertia. That's actually technically a little bit different. That has to do with the density of the object as well. So on the next page, he just defines it. And that's, this is exactly the definition you'll use. For example, let's see how good of an artist I am. Let's say you had a beam that looked kind of like this, like an I-beam. And then it goes back in the distance here. Oh, well, anyway, not exactly a good artist, but so what'll happen is if you look at that from the side view, it looks like this. If you put a moment on it, that's essentially like saying I have a linearly distributed load, looks like this. So it turns out of this, you'll derive all this in mechanics and materials, and out will pop this term right here. And at first glance, it looks very similar to the one we had before, where, it looks like this. Okay, well, that was supposed to be a Y bar. We had this. Now all he's doing is he's defining something new and putting a squared up here on top of it. So it's just mathematics. That's all it is. And to give you a case in point, I think, was it this one? Was it that one? Was it that one? Oh, it was this one. So let's take this one, for instance. This one, we went back, unless he does it in the book. He probably does that. If he does it in the book, we'll just stay. He's got to do, well, there he does it right there. Okay, so we'll stick with that. That'll save us a little bit of time. So he defines all this. And then most of the time, you'll be using this one or this one. There are cases where you can find the J, which he calls polar moment. Again, he's saying of an inertia, but sometimes it's referred to as the polar moment of the area because it has an area right there. This is associated when you twist a beam, or it goes through a twist. So the next thing he does is he says, well, and I don't know why he introduces it. Somehow you have to introduce this stuff. Next thing he does is he says, well, let's come up with the parallel axis theorem. So these two things, parallel axis theorem would probably be the one thing that you're going to use over and over and over. And so what he does here is he says, and the way he's describing, he just says, put two coordinate systems on it. One here and one here. So he's got an X prime and an X. And so as it turns out, you can find, in this case, he's looking for IX about some point here or some point there, which is the centroid. So this is the centroid of it. This is some other spot that's not the centroid. So what he's done is he said, well, let me just define a distance y, because this is this, you know. Okay, so if it's just y, where you're going up, say you're going from here all the way up to that little D area there, then essentially that's this is y. This is the same thing as this value, which is a constant, times that value. It's just simply not times, but added to that value. So in other words, y is equal to dy, which is just a distance, plus the other coordinate system. This is the coordinate system that originates at the centroid. So if it's originating at the centroid, it's a special spot. And we'll talk about that in a second. Next thing he does is he says, oh, well, this can be broken apart into y squared plus 2, this times that, plus this squared. Well, dy is just a distance. And so it was originally in there, but because it's constant, it can come out. And so if you look at this mess, what you'll see, and let me get a lot of this out of here. What you'll see is this term, but then if you pay attention to this term real close, what you'll find is this is like asking what is the x and y coordinate of the centroid, because this equation looks just like y bar is equal to integral of y d area over that. Now, if you look at that term and you say to yourself, I'm putting my coordinate system on the centroid, in other words, have this blob. Somebody puts a coordinate system at the centroid and asks you, what's the y bar? It's got to be 0 by definition. So by definition, that one goes to 0. And what you end up with is on the next page is the parallel axis theorem. Okay, what this one is it's the Ix at the centroid. And this is just area, or the distance squared times the area. And so consequently, that's what you see. Area times the distance y, and then what you would look up in the table here, and I'll show you that in a second. And so let's see if I can do this. You can't do that. Can you do that? Nope. Just got to. So now what he's done next is he's decided to make okay, so if you take this sounds weird, but let's say you have an object or something, and it has a certain Ix about it. This is like it doesn't make sense, but it's like taking all the area and sticking at one spot, some distance. In this case, it's got to be the y. So you take the Iy, divide it by here, and basically you'll get that distance. It relates back to the parallel axis theorem. What you're doing is taking all the area, you're moving it a distance away, and then that's what this distance right here is. So if you take this, let's say ky squared times a equal to Iy, that's as if you look at it, that's as if you had kind of like a black hole of area. Sounds weird, but all the area is concentrated in one spot, but then you move it away. It doesn't make logical sense, but it is just a term that they use. Sometimes manufacturers will give you that. All you're looking for is trying to find this. So if you were given the ky, you just basically Ix is equal to area, or whatever it is, times ky, the value that was given to you. It's just the definition of a term. Don't try to make too much sense out of it, but it actually came out of the parallel axis theorem. So let's take a look at this case. So he says, determine the moment of inertia of a rectangular area passing with this picture with respect to the x prime axis, which is that one, the xb passing through the base, and the pole or z perpendicular to the x prime y prime plane. Okay, so I guess that's the C, point C, and passing through the centroid C. Okay, that's what he was saying. So all he does first is he comes in here and he says, I'm going to use a particular coordinate system. Just so happens that I'm going to use this one. Well, this one and this one go together. And then what he's doing here is he's grabbing the dA. So since the base of the thing is just B, or this thing is B from here to here, this is dy. That's all you get right there. The B can just be extracted out, and you'll end up, of course, you're going from here to here. You're integrating over the whole box. If you carry this out, you'll get the 1/12 base times height to the third. That is the one equation that by the time you get done with mechanics and materials, you'll probably remember it because it's used over and over. And if you have your book, I don't know if you do, but what you'll find, okay, you've got a few things here, and then you'll find this table. I have no idea what page that's on. It doesn't even have a page. But take a look at it. What you'll see is a lot of these came up in your future. You won't necessarily be integrating these. You could if you wanted to, but in the future, most things that are manufactured are either this or a combination of. There is a possibility of having a cap on the top, and I guess you might have something like here. A quarter circle is possible, depending on what you're dealing with. But the most common of all these, definitely the most common is that one. I'd say second is that one. There are a lot of cases in fluids that you end up with this one. But for the most part, I would say these four. And if you're essentially, you're not going to be re-deriving these things. So often they're just given to you in the back of the book. Or the back cover in this particular case. I went too far. So if you look at this, he ends up with the 1/12 base times height. Then what he says, and this is an important part right here, and we'll compare this to something in a minute. He says, and let me get the width up. He says he wants to know the moment of inertia about the base of the triangle. And so here we found this one about here. That's this. Notice it has a bar on the top of it. This one does not. So it's basically saying, take this 1/12 base times height, multiply times the area, which is a base times h. That was supposed to be a h. And then d squared, the distance to it, and you'll end up with what it would be down there. One way to think about this, and an interesting thought process is, and this might relate back to moment of inertia. When you think of these I's or whatever, think about it as though, here you got, this term he's basically called I bar X. Technically, it's XX. So if you think about it, put a bar right through here and spin it around here. If you spun it in a circle, you would have to have a torque in order to get it to spin up. At the same time, the larger the momentum is, the slower, more time it takes to spin up. If you're down in here, You're basically spinning. You would think if you're spinning it around here, it's going to be harder. So the further away I spin it, so if I connect this thing to a weightless rod right here and spin it about this axis, I would assume my eye would be larger than spinning it about this axis, and this would be the smallest. If I spun it about this axis, you would find that it would be as if you were spinning it about here. The inertia would be the same. And in fact, that's the case because the distance is squared. So the smallest eye is at the centroid. If you start moving away from the centroid in either direction, the eye becomes larger. And so that's in fact what you see here. You had 1/12, now it's 1/3. And so the further and further away you go, the more you, the larger this eye becomes. And part C, what is he looking for? Polar moment. Okay, first, if he's looking for the polar moment, he's just adding these two together. And so polar moment means it's about a point right here. So it's no longer about just an axis here, an axis there. It's where the axes come together. And so I can leave you with trying to solve some of these. That's fine. It becomes kind of a headache if you start looking at it. Let's look at just this one. I can show you why it's a headache. So what he's done, or let's start with that one. So what he's done is, you notice he has two bars. He has a vertical bar and he has a horizontal bar. And the thing he comes in is he says, well, first he's wanting to find the IX. So you got your IX here and then your IX down here. Notice something interesting about this. Okay, for the top one, he just has, I don't know how come it's, he has the equation. Nothing wrong with that. The equation's sitting right there. It's not a big deal. He turns out that, okay, if I pull this off right here, that matches this where it's that way. And then he goes in and he has to use, see, he has an X right here. He can't use that. He has to use this in order to embed that and replace that back down in here. Once he does that, he can carry out this integration. He gets a number. So everything is fine, and you think everything is good, and then you go to the next case. Now, notice what he does here. And this is one of the things you got to be careful of. This is why I like case 1 better for the X. If you notice case 2, the bars are vertical. And you notice what he does is he basically says this, and then he's going ahead and picking this up, which, believe it or not, take a real close look at this thing. Looks like that. Okay, this is the 1/12 base times height to the third. Your base is this, your height is that. So if you notice, base times height to the third. And then he has to do a dA times y bar, which is the y bar is halfway up, because that's where your centroid is. So he has to use the parallel axis theorem on that one. And he also has to use it's as if this little sliver were spinning about here. Now oppose that to the other case in which, yeah, you do the same thing. All of it, you could basically say this is basically a line element spinning about here. You don't have to do any of that right here. There's no 1/12 base times height. So the moral of the story is you can make the problem harder or easier. If you're doing IX, you want to do horizontal bars. If you're doing IY, you want to do vertical bars because you don't have that complexity. Let's see if I can get down. Oh. Okay. So then all he's doing is he's taking this and inserting in here and carrying out the integration. Now, of course, he worked himself across to finally coming up with that. It turns out he should get the same answer, and he gets that same answer here up at the top as he does right here. But this one required a more complex situation to get it. Maybe a way to, no, there's not a way. Now I don't know what to do. How do you make it go away? Oh. So again, you go in here. Okay, so this is the nice way. Case one, simple, straightforward. Basically, he comes in here. He has to define dA. So what he's done is that. And he's looked at the differential element like that. Had to, got a complexity out of it because, first of all, your x went the same on the left as it did on the right. But then you've got to use the equation of the circle to replace the x as a function of y. And so you got to x is equal to a squared minus y squared in the square root. Gets stuck in right here. And then you carry out the integration. Case two, you got the same thing you did before. And that is somewhere, well, it turns out, first of all, you doesn't have to use the parallel axis theorem because as you're scooting along the axis, it's halfway to the top and bottom. So all he has to do is 1/12 base times height to the third. The height now is this one and this one together. So he has this, then he takes it in here and integrates it. So you could integrate it. In this particular case, you have a y, which is a function of x. So you need to replace that. So you need to come in and say y to the third is equal to, I guess you could say, the third power of a squared minus x squared. So it kind of gets stuck in here like that. And I guess you could take the third and the square root and you could get 3/2. You get the same answer either way. But if you're looking at vertical bars and finding the I about this axis, it's harder. However, if you're taking these vertical bars, it's easier to find I about that axis. So and then he just has a bunch of problems. That's all fine. However, this is the part that's the most important, is composites. Okay, and he just says the word composite, goes on about it. So let's do a composite section. Let's just do that one. And so if we do that one here, I think we got enough. We probably have enough time to do this one. So let's do it. Then we'll come back and take a look at, uh-oh, I don't have the snippet up. We'll come back and compare what we've done and the way we've done it. So what we'll do is he's already identified. So this is what we're looking to find. I don't like that color. So this is what we'll label as A, and this one is the one we'll label as B. Now the other question is, I need to know if he wants to find it around the X. Determine them on about the X-axis. So there's your X. So, okay, so he does. He wants to find it about here. So what I need to do is I need to list, I have region A, region B, and make myself, whoops, a table. That's not what a table looks like, okay? So first of all, I'm going to hit this with area. That looks funny. Area. So I'll look over here. What is that? 100 by what? 150. And I don't even have enough space. So do that. 100 times 150 is 150 and 2 more. That's for A. B is, oh gosh, here. This is not going to be. Okay, B is 25. Okay. Is that the radius? Yeah. 25 squared times here. Oh, let's see, 1963.5. Good enough. Did I copy that right? And so down here we'll have the total. I'll go ahead and do this just out of curiosity, you know. I probably shouldn't, but then I'll basically put up here, let's see, I'll need to have A times dy. So I'll put a dy right here, dy squared that is. The distance from here to the centroid and the distance from here to the centroid. Turns out in both of those, it's 75. Then what I'll need is I'll need a column that says A dy squared. So these numbers are not going to be small. So 0 times, what is it, 75 squared. Oh my gosh, okay, that's 84,375. 84, 375, 000. Is that right? Yeah. Okay, so let's do the last one, which is that one. That 75 squared there. Oh, geez. Okay. 11 044 662. How about that? 662. So I've done, this is the part I needed for the parallel axis theorem. Now I need to put in I bar XX for each object. Here's where I go to the back of the book. And I'm going to skip over this. Let's see. This is page 527. I can come back here and look and see how I did. But I need to get to the back of the book where those tables were. And I need to recognize, okay, that I only need this one. And I only need that one. So it's 1/12 base times height. Let me find the book. Okay, so for A, 1/12, the base of this thing is 100. The total height is 150. And if you look, base times height to the third. So that's about its own centroid. And that's the key there. Okay, so I'm going to use MATLAB to figure that one out. 100 times 150 to the third, not squared, divided by 12. Okay. 28, 125. 28, 125, 000. So that is the number that goes here. Then the next thing I need is for B. B is little bitty, but it has that 1/4 pi r to the 4. 1/4 pi r to the 4. So let me 1/4 pi r to the 4th is equal 1/4 pi r is just 25 to the 4th. That number, let's see, pi times 25 to the 4th divided by 4. Okay, 306,796. 306,796, I think. I don't need these other things down here. I think it, uh-oh. Okay. Here, I'll just go to here. So at this point, what you have to realize is I subtracted the whole. Looks kind of funny. So in fact, I can't go down any further for some reason. There we go. So in fact, what I need to do is I need to find the I of A about that XX, I guess you could say. So I guess I better write it like that. And then take off the I with a B about the X. So, but I've got to add these two together. So in other words, here, let me do it this way. Let me first determine each one. And now maybe I can just resort back to his example, because then I'm just looking at a bunch of math. So if I do that, that might speed us along. 527. So look at what he did. He came in, he did composite parts, okay? The area can be obtained by subtracting the circle from the rectangle. Centroid of each is located in the figure. So it's what he's saying is there's the centroid and there's your centroid. So then he says parallel axis theorem. He does the circle first. What he's doing is he took this component and then he took that part right there, which is the area times the distance. And he got this value out of it. Now that's what I should get if I take, okay, B, that would be this number plus this number. It should be 1131, something like that. Is that what he got? 11.3. Okay, so yeah, 11.4, I guess maybe. So if you add these two numbers together, 11, and he's doing a 0.044662 with 10 to the 6th, and then 0.306.796. You add those together, he's saying it's 11.4, which I've got slightly different value, but that's okay. Then what he does is he does the rectangle. And he does exactly the same thing. He finds the I about the centroid and then does the parallel axis theorem. And he gets a fairly large number there. So if we did that on ours, do we get that? 80. Okay, so if I add 28.125, which is from here, and then 84.375, I have no idea what I get, but let's find out. 28.125 plus 84.375 gets me 112.5, or roughly 112.5 about. If you look back at the book, he gets 112.5 right there. Then what he does is he subtracts the two of them, if I can find them. Okay, so what he's doing is he says, I take the square, I subtract the whole out of it, and that gives me the area moment about it. So to me, I like the concept of the table better because I can keep track of each part. I can write the area down. I can determine this value, then square it, and then list this out. And then I can add these two. So in fact, you could probably do this in Excel spreadsheet this way. And that's pretty much it. Now there's a little bit of complication to it. Let's take a look at one more, and then we're getting close to the end. Here he has one where he's identified three different, an A and a B and a D. And I think the reason he didn't pick C is because the centroid is listed as C a lot of times. So he says rectangles A and D are similar in a way, and he lists them out. So he takes the 1/12 base times height, the base times the height, base times the height. He has, this tells you the IX about that location and about this location. Then you need to use the parallel axis theorem. I take the area, 100 by 300, 100 by 300, that's the area. And this is the distance you're moving it, or the 200 meters that you're moving it here. Same thing here, you're moving it 200 meters back to the, so you're essentially moving it back to the origin. And then he gets that value. So then he does it for y as well. What you have to realize is you have to tilt your head. If you're tilting your head, what becomes the base and the height then? The base now becomes something different. So if you're tilting your head sideways and you're looking at, say, this block right here, if you tilt your head, this becomes the base and this becomes the height. So this is the base. Now this is the height. And of course, these are the same, but you're moving it 250 back to the, so you're moving this point back to this point. And that gives you that value. And then rectangle B doesn't have to move anywhere. It doesn't need the parallel axis theorem because the origin's already sitting right there on the centroid. And so you just basically say, hang on. You just basically say 1/12 the base of the whole thing. This thing has to be 600. So let's see, 250 and then another 250, 500. That's half that. And then, yeah, so 600 is the base. The height is 100. So this has to be 100. I don't know. You see it listed anywhere. Oh, yeah, it's listed right here. Okay, and then what you do is you're looking for IY. You turn your head sideways, and this is vertical, and this is left and right. If you're turning your head perfectly sideways, the height and the base swap, and that's essentially all you get, is you get a smaller number and a larger number. Then what you do is you're adding them all together. Let's see if I can get rid of all this other stuff. So you're saying, well, first of all, he's basically, let's start with X. You have two of these, one here and one there, two of those, and then you have just one of these. You add them together, and that's your I about that axis. If you tilt your head sideways, you're taking two of those, that, and then simply one of those. And you're putting them together there. So the composite section is just a little bit of patience on it. And so here I have some videos on some of these. I think I did that one in the video. I think I did this one in the video. Once you see one or two, they all look the same. And so there's no need to cover. So that's essentially it. Most of anything that's asked on the final is going to be composites. So I guess I'll claim I'm done, and I'll spend the next few minutes going and getting the videos from the other, and I can't ever remember where it's at. So if I go to the playlist and then statics, okay, wait a minute. So there's one. Let's see. How do I get that? Okay, so here's composite sections. Oh, so I wonder if I can copy that playlist. How do I copy the playlist? Who am I right now? I'm that person. Maybe I could copy this. I know. Let's see what happens if I do this. I just go to Blackboard and paste that link. I wonder if that would work. Let's try it. Go to statics. Then make that thing come back. Content. And then build content. Oh, come on. Link. Web link. Okay. Okay. Deposit videos. Let's see what happens if this works. Okay. So where's all this junk? There's nothing else to do except that. Hit that. Submit. Now go to the bottom. Get the thing off the bottom, because I don't know why they do it, but they put it at the very bottom. And now, if I just click it, it takes me right there. It should. No, wait a minute. Is that the playlist? Watch. It just says watch. How the heck do I get the playlist out of it? Okay, wait a minute. Go back one thing. Copy link address. If I did this, what would happen? Paste and go. Am I watching a playlist? But that's what I had before. List. Oh, that is. So you're watching the playlist. So then you could go down and click one of the other problems. So here's that problem. Oh, why did I go? Oh, anyway. So there's that problem worked out. So I think those 4 videos, I guess either 3 or was it 4? 4. So it's problem 1029, 1030, 1040, and I have no idea about that one. But that says 1030. I don't know. That says 1030. Oh, you know what I did is I did. Well, now wait a minute. Did I put the video in there twice? Okay, get all done. Oh, that's what it is. That's the same as the first. Now I'm playing the second one. So there's 3 problems in there. So what I do is I always build a table. So on the test, I'm going to write the table. So you have the table. Then what I'll do is I'll come in here on Monday, or probably just Monday, and I'll make a take-home part of the test. So you by all means you want to work that, if you know what I mean. So, but I'll just do it on the OneNote, and then I'll pull it off OneNote and put it on Blackboard. So you can pull it off OneNote or Blackboard, whichever one you want to do. And so that's it. I don't know. I'm not sure if I'm going to ask anything on friction.